So this is, I believe, the fifth in the series of video-based lessons illustrating the application linear programming in chapter 14 of the textbook. Um, this and the next slide will illustrate the multi-period production planning models that involve making decisions on how much to produce and store in each time period to meet the anticipated demand in each of those periods while minimizing the overall production and inventory holding costs. Depending on the structure of these costs, it may be possible to produce more in the periods with low production cost, store the product in inventory, and still come ahead in terms of the overall cost at the end of the planning horizon. Other times, and this is an example we have for this video illustrate this pretty clearly, other times just-in-time production with minimal or no inventory may yield better results. The inventory holding costs, especially for the longer horizons, should but often do not include the potential cost of inventory write-downs due to changes in the demand or products becoming unusable or obsolete and so forth. So, K&L Designs, right here in the bottom half of the current slide, is the fourth of a set of Chapter 14 models, the template for which, again, is contained within the Readings subfolder of the 04 Applications folder. Although I'm not going to go through the 8th Chapter 14 exercises in either videos or classes, they are great examples you should do on your own as part of your chapter readings. Okay, so just briefly, K&L is faced with a decision on how many jewelry boxes to produce in each of the three seasons, autumn, winter, and spring, to satisfy demand at the lowest cost, while also satisfying the so-called balancing constraints, the last type of constraints we want to introduce, or we did introduce at the beginning of this series of videos and want to expand on in this one. Okay, so this slide sort of visually shows this. So when dealing with multi-period models, it is often helpful to create a multi-period production / inventory flow chart. And I sort of gave it that name, such as the one shown on this slide over here, right? Each of the boxes represent a specific time period, okay, with arrows going in, such as these guys, and these guys, representing the initial inventory at the beginning of the time period, okay, as well as the production during a particular period, right? And then inventory at the end of a given period as well, right? And arrows going out, right? Like this one, right? This one, and that one, represent the demand for that period, which is given literally here with numbers, as well as the remaining inventory at the end of a period, which then represents the beginning inventory of the next period, where the same story repeats. So that's what's sort of neat about these production / inventory / demand flow charts. Such as the one in K&L Design's example, right? So in this slide, the capital I clearly represents inventory, P is for production, right here, and the anticipated demand is listed as actual numbers at the bottom, as I already indicated. If you pick any of the time periods, it is easy and intuitive to construct a balancing constraint. For example, for winter, right, IA is the beginning inventory, because IA was defined as the inventory at the end of autumn. PW here is the winter production, so the sum of those two, okay, have to equal the winter demand of 400 plus the inventory, the remaining inventory labeled IW, which then becomes the beginning inventory for spring. So the equation IA plus PW equals 400 plus IW comes out quite easily, and that is, the classical, typical example of an inventory balancing constraint, right? So the same goes for the other two periods, right? And noting that I0 equal to 0 denotes the initial autumn inventory of 0, which in general does not have to, and typically isn't the case in reality. Okay, so our multi-period production example is almost exactly the same, except for the added production, right, along the top of the chart, and storage capacity constraints towards the middle of the chart here in each of these time periods. Okay, the question for the pigskin company in this Lect 4 multi-PR prod Excel file is how many footballs to produce each month for the 6-month planning horizon in order to satisfy the demand without exceeding the production and storage capacity at the lowest possible cost overall. Okay, so the flow chart, again shown here, looks very similar to the one from the K&L design. The main, again, difference is that the K&L design had a shorter time horizon of 3 seasons. Here it's 6 months. So in real time frame, right, the 3 seasons is 9 months, more than 6, but in terms of complexity, this one has 6 nodes versus 3 over here. Okay, so let us open the lect4 underscore multper prod, all right, Excel file. And let's come up with a feasible production plan for each of the 6 months that will satisfy the demand without exceeding the production and storage capacity. Then we'll calculate so we'll do this separate, and then we'll calculate the cost section at the bottom of the model, and then we'll see how to improve on that by basically setting up and running the solver model. Okay, so because the production costs, look at them right here in the row 8, are lower earlier in the planning horizon, and the inventory holding costs are, based on this 5% here, proportional to these production costs. Let's produce a little bit more, not as much as we can, but a little bit more early, store the excess, have some inventory, and see what happens later on, how that pans out, right? So notice that there's an initial inventory of 50 units. Notice the production capacity of 300 and storage capacity of 100 repeated. Although that's not necessary, I chose to do it for simplicity of then formula creation. And then notice the demand, of course, varies from time period to time period over here, right? So with the initial inventory of 50 units, right, let's, for example, produce, I'm going to scroll down a little bit, 150 in first month. Okay. That is clearly under the production capacity of 300. It's actually the 50% capacity. So after the production, we would have the initial inventory of 50 from the top, plus the 150 for 200, and then the demand would reduce that 200 by 100, okay, to an ending inventory of 100, which is the maximum we can store. Okay, so it's not the maximum we can produce, obviously, but it's the maximum we can store based on the relatively low demand in the first month, compared at least to some of them downstream or midstream, I suppose. And then let's suppose this is a first sort of step. Okay, so that means that the ending inventory of 100 units becomes the initial inventory for month 2. Okay, so if we assume they'll produce the same amount of 150, again, sort of mid-capacity level, right, out of 300 in month 2, then after production, what we have is the 100 we started with here, plus the 150 that's produced, and then we'll just move this formula by copying it to the right, and again, end up with 100 in inventory. Okay, notice now the demand sort of ramps up, basically doubles from month 2 to 3, right? So the production capacity, we have to remember the production capacity is capped at 300. So, this is the most we can produce, and let's do that, because again, still keeping in mind that production costs are kind of low at this point, right, or lower than per unit than later on. Although the differences obviously are relatively marginal, but they do compound. Then I will again, in this case, just copy these two formulas up to the right, Control R, to get to the 400 on hand after production, and then satisfying that demand would again have an ending inventory of 100, right? Okay, so for the month 5, okay, again, let's produce as much as we can because the demand keeps going up. So let's produce 300 units again. So that should then allow us to copy these formulas again, right? So on hand after production is 40, with only 50 left at in inventory because of that increase in the demand, right? So notice, right, the production constraints are observed and the storage constraints are observed. Okay, for the month 5, okay, because the inventory is slightly, is going down slightly, okay, but we're going to have some demand, obviously. I mean, demand is going down slightly, but we'll have some in month 6. So trying to think about both months, let's still produce as much as we can, 300, okay, which then gives us the 350 on hand, which is again more than enough to satisfy demand and leave 100 in inventory. And then let's just not produce at all in month number 6. Okay, and we can afford to do that because we have 100 units in inventory, which then exactly satisfies the demand, leaves us with no inventory left at the end of the planning horizon. So that's sort of one way to sort of gobble up or cobble up a feasible solution in terms of production and storage capacity constraints, right? So in this production front-loaded resulted in relatively significant inventory. It's pretty much at the maximum, except in month 4 and at the very end. Okay, although no production was scheduled for month 6, that's that 0 over here, there's a considerable inventory holding cost, right, associated with this strategy, as you might imagine. It remains to be seen if the offsets the lower production, or literally no production at the highest cost in month 6. Okay, so before we can evaluate that, obviously we're talking about dollar amounts as well. We have to evaluate or calculate all the associated costs as well as the total costs, right? We'll start with production costs, okay, and we'll multiply from month 1. Okay, we'll start with production costs and we'll multiply unit production with number of units produced in a month simply, right? So production per unit times number of units produced. Okay, and we'll copy that all the way to the right. And then for the holding costs, we're going to take the 5% of, which means multiply, of the production cost per unit, fix the blue cell, right, so it doesn't slide. Okay, and that's our unit holding cost, or inventory cost, and then times number of units held in inventory, which we know is sort of almost maxed out, right? Although these numbers are, of course, comparably much smaller than the production cost, which was sort of the idea, I suppose. And the total cost on a month-by-month basis is adding the production and inventory. Okay, then adding all the production costs to have that value on the right-hand side, as well as the total holding cost, and finally the total overall cost of about $15,500 or so dollars, right? Okay, so the solver, right? So this is our sort of baseline. So the solver model minimizes this total cost cell H22, right? So let me zoom in a little bit. I should be able to do that, and then minimize that cell. Add-ins, premium, solar, objective, add, and make sure you minimize it by changing, right, the production decisions in range here in the 14th row between columns B and G. Okay, and then the demand, production, and storage constraints. So there are 3 constraints. Okay, the demand, okay, is satisfied by requiring the on-hand amount, this guy over here, after production to be at least the demand, which is in row 10. Okay, so the demand constraint requires that on-hand after production, right? All right, I know, this sort of assumes that the production takes place all at once at the beginning of the month, which obviously it doesn't, right? So it's obviously simplified. But if looking through a lens of a month, this does make sense. On-hand inventory, on-hand after production is greater than or equal to the demand. Okay, then the units produced, right, themselves, or the production, is subject to the capacity that we were monitoring pretty diligently of 300 units per. Again, we didn't have to repeat this number 6 times. We could have used a single number. And then finally, and it's just a simple bound constraint as the solver shows. And then finally, the ending inventory has to be under the storage capacity of 100 units, shown right here. which is another bound type looking constraint. Okay, so making sure that unconstrained variables are negative using the LP. Okay, and solving, we'll see that we have a marginal cost improvement of about 120 bucks, I believe it is. Okay, we'll pick the answer in sensitivity report, just in case. I'm not going to discuss it too long, but not a little bit. Okay, so again, the result solution achieves about 200 in savings, as I just indicated, right? From 13, and not even that, 150, by not fully front loading the production. As a matter of fact, producing just enough to satisfy the demand in the first month, as you can see here, having little inventory in months 2 and 3, right, and then producing just enough to satisfy demand in the remaining 3 months yields apparently the best possible solution, mitigating the cumulative effect of keeping too much on inventory versus producing more in the more expensive production months towards the tail end of the planning horizon. And this is obviously, even for the simple model, hard to sort of anticipate, right, how that dynamic sort of plays out. But this is sort of an argument in favor of more of a just-in-time approach versus piling up the inventory as we started with, right? So looking briefly after moving the tab at the sensitivity report, okay, and zooming in so you guys can see this in the video, moving down to reduce cost section and highlighting them, we're going to have to add the pennies here for sure. Okay, shows the two non-zero reduced costs actually, and those are actually the shadow prices associated with the production bound constraints, which is not easy to see here. Okay, however, the allowable increases and decrease ranges refer to corresponding objective coefficients, these guys over here, right? So this is a little confusing, right? This is a little confusing, and that's what one of the examples in chapter 14, J&M manufacturing, shows how to deal with this issue, right? By using the auxiliary decision variables, referencing the decision variable cells, which then allows for the bounding constraints like the production capacity to be included in the sensitivity report, whereas right now they are not. They are not. Okay. The interpretation of the shadow prices further down, right, are a second typical example with some pennies here. Okay, for the demand and storage capacity constraint is not what we would like it to be either. Okay, if you look at the right-hand sides, okay, look at the right-hand sides, those are not the original right-hand sides associated with the demand and storage capacity of 100 units, right? For example, an increase in demand will reduce ending inventory, which will increase production, making on-hand after production higher, etc. in this sort of closed iterative loop, right? The same sort of circular logic can be applied to the increase in inventory storage capacity. So there's no way for us to use the shadow prices properly in such a formulation, in such a model. This is really because changing one parameter changes other cells / parameters that act as parameters to other constraints, invalidating the core assumption of the sensitivity report stating that only one parameter can be changed at a time, okay, to have the correct interpretation of reduced costs, shadow prices, and associated allowable increase and decrease ranges. Again, please see a second example called Walker Wines at the end of the chapter for more detailed discussion on this issue. Okay, so this let's save this changes here, switch to the PowerPoint, and this is a good place to pause.